Namaste. Let us start the next lecture of week 7. In this week, we have started talking to you about nanomagnetism, meaning what will happen to the magnetic materials and their responses when the particle size of these materials go to the nano scale. More specifically, if you are talking about materials which are in the dimensions of 1 to 100 nanometers, then will the magnetic properties change, and if so, what would be the reasons behind it. In the first lecture, I gave you the understanding as to why there would be changes in the response characteristics of magnetic materials. We introduced to you the concept of elongated and elongated grains. Now, let us start the next lecture today and see some more properties, how they can change, and once they change, what are some of the characterization tools which are used to estimate the changes in the properties. Because it is also very important to understand that you should have the capabilities to measure a desired property or the number of properties which you expect would get modulated in any given system. In this case, let it be magnetic materials with nano size dimensions. So, in today's lecture, we will talk to you about the characterization techniques, some of which are very simple to understand, but their actual implementation in the laboratory or industrial level needs much more investments, and you need highly trained people to operate them. You will find that there are techniques which would also be based on the concept of quantum tunneling and thermal activation in these magnetic materials, which can also show surface and size effects. And time permitting, we will like to finish by giving you some of the important applications of these nano sized magnetic materials. So, we have seen till now that if you talk about nanostructured magnetic materials, then they are made up of magnetic grains or particles with dimensions typically below 100 nanometers and more than 1 nanometer. So, we are talking about the same 1 to 100 nanometer range. When you talk about these magnetic grains, we have introduced to you in the previous lecture the concept of elongated grains. And if you will see that these materials would have different properties than their bulk counterparts. This was something which is told to you in the previous lecture, and repeatedly we are telling you this, and then we build the theory on that. This is basically coming from quantum confinement effect. But if you look into the concept of elongated grains slightly more in detail, then what will you see? You will see that if I have a grain, then I may have large number of grains in this elongated grain. Now, what do you see from this figure? This figure is showing to an extent that these grains are arranging themselves in one particular directions, and mostly they are near the surface. This is one thing which is becoming clear to you, and the moment this happens, you can immediately say that the surface atoms will start playing a critical role in deciding the properties of such materials. As we have already seen that once we go to small sizes, then we are talking about the concepts of energy quantization and electron tunneling. But now comes another question. If you have such ordered structure and they are very thin, that means they are in the nano dimensional range. Now, these domains consist of particles, particles are made up of atoms, and atoms are vibrating around the mean position in the lattice arrangement. Now, if you have a large particle and increase the temperature by certain multiples of T, then the thermal energy gets added and you see an increase of delta K beta T. That means you have K beta T is the energy, thermal energy, where K is the Boltzmann constant. Now, if you go from T to T1, then in this point the energy is K beta T1. But if most of the atoms are on the surface and you have a very thin confined systems, then thermal variations can impact these properties significantly, and hence thermal energy becomes comparable to magnetic anisotropy energy, which although there is some kind of an ordering and you expect that there should be ferromagnetic type of response, but you do not get a ferromagnetic type of response, you get something like a super paramagnetic kind of response. So, if you have an MH curve, you get a super paramagnetic kind of response. So, thermal energy also become very important parameter in determining the properties of such materials. These magnetic nanoparticles, because of their very interesting modulation in response characteristics, are now finding large number of applications. It ranges from medical to multifunctional multiferric type of properties to various other kind of properties which are mentioned here. So, you see lot of applications which range from data storage, sensors, biomedical or even magnetic energy storage systems. So, if you look into the whole concept once again, what is the thing which will come into picture? If you are talking about elongated grains, then you are basically talking about uniform magnetization which will display high coercivity, and because of this the domain wall formation is energetically unfavorable in nanoparticles. Otherwise, if there are domains and subdomains, then you would have these domain walls forming, and again then these structures would not align easily. Therefore, domain wall formation becomes unfavorable, and the moment you go to nano sized, then thermal fluctuations become important. They can flip the magnetization, introduce some kind of randomness resulting to a super paramagnetic type of behavior. Please remember, super paramagnetic materials are very useful in transformer oils and those kind of applications. And these particles, these super paramagnetic particles, they exhibit very low or 0 remnants and very low or nearly 0 coercivity in absence of the field. So, in this whole system there is another concept which becomes important, that the relaxation times become important in determining the dynamic response, because how your system, if the temperature increases, let us say thermal energy increases, then the vibration, lattice vibration or vibration of the particles, they have different magnitude, then how do they rearrange or distribute energy within the system so that they can maintain the state. So, it becomes very important to understand the relaxation times which will control the dynamic response in such materials. One of the first technique which is extensively used to determine the properties of such materials is SQUID. This stands for superconducting quantum interference device. So, you can perform SQUID magnetometry to measure even very small magnetic fields, and it operates on the concept that you can have quantum interference effects in superconducting loops containing Josephson junctions. For carrying out the measurements, you can go up to 4K using helium, liquid helium, and then you can determine the magnetic moments as low as 10 raised to the power of minus 8 EMU, which makes them ideal for determining weak magnetic signals in such nanomaterials. So, you can go to very low temperatures, that means you can minimize the thermal effects, and then you can find out what are the magnetic signals of such nanomaterials. How do you perform such measurements? They are very simple measurements. It is the whole setup may be an expensive setup, but the operation is not very difficult. Once you learn it, you can easily do it, there is no problem in that. So, you have to take a sample and place it in a uniform magnetic field, and which is moved through a superconducting detection coils. Now, as the sample moves, what happens? It induces a current in the coil that is detected by the changes in the magnetic flux. Now, the change in the flux is converted to a voltage signal, which is directly proportional to the magnetic moment of the sample. So, higher is the change or signal that is the voltage signal is higher, you are getting higher magnetic moments. You can have both modes, DC as well as AC magnetic susceptibility measurements. And now suppose you perform the measurement at 4K, you can perform the measurement at 10K, 20K, and hence you can carry out the measurements as a function of temperature or varying fields. So, you can determine the magnetization. Because of the use of such superconducting detection coils, you have very low noise, high resolution, and making this technique a versatile technique for carrying out fundamental studies in superconductivity and spintronics. Yes, squids are expensive, which can sometimes limit their accessibility, but if you look around now in India, nearly all central universities, major institutes, and many of the privately funded institutes where research is also being carried out, they have squid. So, it is no more that their accessibility is limited, but you have to then talk to people and get access to this measurement, and you can determine the properties of the nanomaterial which you have synthesized. The next much simpler and less expensive technique is the VSM, that is the vibrating sample magnetometry. So, what do you do here? You measure the magnetic properties of the material by vibrating the samples near a pickup coil. Now, a sample is magnetized using an external magnetic field, and then it is vibrated at a known frequency. What happens? The motion of the magnetic sample induces a voltage in the nearby detection coils due to the Faraday's law of induction. So, you get induction taking place. Very simple. If I ask you a question, what would be the induced voltage? Clearly, the induced voltage would be proportional to the magnetic moment of the sample, and immediately you will be able to quantitatively determine the magnetization in such samples. Here also you can carry out MH curves or you can have empty curves. This technique can be used for nanoparticles, thin films or even bulk ferromagnets. Generally, VSM is performed at room temperature, but nowadays you have such systems where you can carry out measurements at low temperatures as well as slightly higher temperatures than room temperature. VSM, as you may have seen, is not using superconducting coils or anything like that. So, they are less sensitive than squids, but they are easier to operate and less expensive. So, become more affordable. And using the measurements, you can then draw the magnetic hysteresis loop. From there, you can find out the coercivity, remnants or saturation magnetization. And this is one of the most common techniques which are used to determine the magnetic properties of the materials we are discussing in this week. Now comes the concept of quantum tunneling and thermal excitation. If you look into, let us say, a particle which is incident on a system or a barrier with an energy more than the energy of the incident particle, then classically what would you expect? You would expect that the particle will not be able to cross this barrier. But quantum mechanically we can show that there exists a probability that even in this case the particle has finite probability of crossing this barrier and moving forward. So, this process is called as quantum tunneling, and this phenomena becomes quite dominant at low temperatures and when we talk about small size particles. So, what you will have that in simple terms you will find that the particles can pass through the energy barrier rather than going over it, and this phenomena is called as quantum tunneling. So, each magnetic particle has two preferred directions, either upspin or downspin. So, you have upspin or you have the downspin, and hence you get a double well potential, meaning that both these states are possible. Now, if the particle is small, and you are at very low temperatures, the particle can go from one magnetic state to the other without the need of thermal energy. So, you do not have to give any thermal energy, but the system can flip its direction, and the rate of tunneling depends on the height of this barrier and also the width of this barrier. So, if you have particles which are at or above a certain temperature, that is called the blocking temperature, here the thermal energy will dominate and they will help in the flipping of the magnetization direction. So, you will have again randomization taking place. Hence, in the thermal regime, what will happen? The transition time will follow the Néel-Arrhenius equation, which relates energy, temperature and switching speed. Now, this switching from up state to down or vice versa are not an instantaneous processes. So, what happens? Because of this, you slowly lose magnetization over time, because you spend some energy in moving from one state to the other. Therefore, one must understand these two mechanisms, because they will play a very important role when we are talking about data storage, where stable magnetization over time is essential, otherwise your data will be lost. And you can relate the rate constant K with the Arrhenius constant, the activation energy required and the temperature with this equation. And you can plot the curve of ln K versus 1 by T, you will get a slope, a negative slope, which will be equal to minus Ea by R, and intercept will give you ln A. So, you can actually determine the whole equation and all the parameters can be determined. Now comes the next effect, that is the surface effects. The reduced coordination leads to the spin disorder, meaning that you will have modified magnetic moment. If you have this, what will happen? You will end up reducing the overall magnetic strength, or the system may become unstable in terms of sustaining the magnetic property. And as particle becomes smaller, we have seen that the surface atoms increase. So, one has to be very clear that what should be the optimum thickness of the system, so that you can sustain the desired magnetic response characteristic in these systems. Otherwise, you will not get the desired functionalities in these magnetic nanomaterials. You will start seeing flipping of the magnetic directions, and you will end up getting response which is other than what you were expecting. Hence, as the particles decrease, we have seen that magnetic anisotropy energy decreases, which is proportional to the volume. Now, what is magnetic anisotropy energy? This is the energy required to change the direction of magnetization. So, if you are at very small sized, then the energy is also much smaller, and hence magnetization becomes easier to change by changing other parameters like temperature, or sample is made to vibrate. So, what will happen when you are at very small size particles? They will start behaving like paramagnets, but with much higher magnetic moments than the paramagnets, and you will end up getting super paramagnetic kind of response characteristics, and you will not be able to retain the magnetization after removing the field. If you look into the blocking temperature which we have discussed, what is happening? In this case, we have seen that the magnetization will flip randomly, and we have also seen that we are talking about a super paramagnetic state. In this state, there is no hysteresis loop as we have been seeing. So, there is no hysteresis loop. At various temperatures also, you see different kinds of curve. So, at a given temperature, you will see and then you go on changing, there also you will start seeing different points. And so, what will happen? The magnetization will not show hysteresis, but will follow a smooth curve described by the Langevins function. And now you can tune the size and immediately the coercivity and relaxation times of these particles can be changed. With this capacity, you can use these materials for large number of applications ranging from storage to medical devices, drug delivery, spintronics, sensors, environmental remediation, energy applications which include magnetic refrigeration and catalysis. So, the range of applications of magnetic nanoparticles are much more exhaustive and extensive than what you may have been thinking till now. So, you can go through these books and these references which discuss more about these topics which I have covered today, where we have talked to you about some of the techniques which are used to measure the properties of magnetic particles as a function of size reduction as well as a function of temperature. We have also discussed the large number of applications where these nanomaterials are being used, and as you make newer magnetic nanoparticles, you will find more and more areas where they will be used. So, I thank you for attending the second lecture of this week. Thank you very much.